Welcome to the first set of video notes for Math 135 at CCD, Introduction to Statistics. We are going to start today by looking at Module 4, Part 1 from the textbook. So this is based off of the reading that I had you do before you get to this video. So in this section, we're going to look at different ways to organize and summarize a data set. We're going to look at categorical data first, and then we're going to go ahead and look at quantitative data. So let's get started. These notes are going to follow along with the Word documents that I posted for these, and that is where you will find all of the data sets that I am using for these notes. So make sure you have the Module 4 Part 1 categorical and Module 4 Part 1 quantitative notes in front of you before you go any further in this video. Otherwise, you're not going to know what data I'm using to create these notes. So the first thing we're going to look at with categorical data, remember categorical data means that the responses that were given are given to us in words or categories. So things like hair color, eye color, on a scale of not satisfied to satisfied, how much did you like this restaurant, things like that are going to be categorical. So we're looking at a data set for this problem, looking at a physical therapist's office and the number of injuries that she saw, or the types of injuries that she saw on a given day. So what we're going to do is we're going to organize our data using a relative frequency distribution. A relative frequency distribution starts with this. You're going to have a column for the different categorical responses you could get, a column for the frequency or the number of times you saw that response, and then the relative frequency, which is a decimal or a percentage of the time that you saw that response. So we're looking at the data set on the first page of the Module 4 Part 1 Notes Categorical. And we have all these different types of injuries in a list here. So I'm going to go ahead in the column for body part. I'm going to start by writing down the different injuries that I see. So the first injury that I see here is a back injury. So on this first line, I'm just going to write the word back. And then the second injury that I see is a wrist injury, followed by an elbow injury. Then I see a hip, a shoulder, after shoulder there's knee, hand, and then groin, and then there's one more that you can fit in the notes that I provided for you. I just couldn't quite fit them on this page. There's also a neck injury in there, so we want to make sure we include the neck injury on that last line of the table that I've given you guys. And then the very bottom row of the table in the notes is a total row. We want to make sure that we're totaling things up as we move along, and we'll talk about why here in a minute. So now that I have all of the different injuries that I saw, each distinct injury, I want to go ahead and I want to count how many of that injury did I see. So I'm going to start with the back injuries, and I'm going to go through the list here, and I'm going to count the number of times I see the word back. One of the things I want to say with this is be careful about crossing things out as you go along to the point that you're not going to be able to read it anymore. There are a lot of times, especially with numerical data, where I'm going to have you do multiple things with this same data set. So if you cross something out in pen and then you're not able to read what that said, it's going to be really hard for you to then go back and do the next problem with it. So cross it out in pencil, use highlighters, do like dots or check marks next to them. Just make sure that you can still read whatever the data value is. So there are 12 back injuries. That's a weird looking 2. I'm going to try and redo that. That's a little bit better. So we have 12 back injuries. Now wrist injuries, there are 2 wrist injuries. We have 1 elbow injury, 2 hip injuries, 4 shoulder injuries, 5 knee injuries, 2 hand injuries, There's one groin injury and there is also one neck injury, so that you make sure you fill in all of those rows. So now our frequency column, that last row says total. So we want to total up the frequency column. Because we have 30 data values in our data set, the sum of this column should equal 30. Right now, if I were to add up what I have, it would equal 29 because I'm missing the neck injury in there. But it should equal 30 when you have everything. So this lets you know, oh, did I miss one, or did I double count something? Because you can easily count how many injuries you should have. Or like with this example, I told you that we have a sample of 30 patients. So you can quickly figure out whether you made a mistake in there somewhere. So once we have the body part column and the frequency column filled out, we're going to move on to the relative frequency column. So to calculate the relative frequency, what I'm going to do is I'm going to take the frequency for that injury. So for a back injury, there were 12. And I'm going to divide that by the total number of injuries. So there were 30 different injuries, or 30 patients total. 12 over 30 is 0.4. Woo. All right. Or 40%. You can leave it as a decimal, 0.4. Ooh, I'm sorry. If you're seeing that, I'm sorry. 0.4 or 40%. Either one is okay, just don't leave it as a fraction. So now you're going to do the same thing for the wrist injury. 2 divided by 30, which is 0.0667. And this brings me to the first thing about this class. I want you guys to always give me 4 decimal places after the decimal point when you have repeating decimals or a very long sequence of decimals. You don't need to go past 4, but if you give me only 1, 2, or 3, then I will be ending up marking off points on some of your assignments for that. Homework, it'll say how many decimal points it wants it rounded to, but all of the homeworks that I gave you will accept 4 decimal places, even if it says it only wants 2 or 3. Everything should accept 4, but just keep an eye on that with your homework. Everything you do for me, discussion board posts, questions, and exams, and your project, make sure you're giving me 4 numbers past the decimal point if needed. All right, moving on, 1 over 30 for elbow. That's going to be 0.0333. 2 over 30, I already found, is 0.0667. Now 4 over 30, 0.1333. 5 over 30, 0.1667. If you don't remember your rounding rules as well, make sure you go back and look at those. I recommend Khan Academy for anything like that. 0.0667 and 0.0333. And then the neck injury would also be 0.0333. Okay, and then there's another check that we can do in here. When we add all of this up, it should sum to 1 or 100% if you're doing percentages. If you're off by a tiny bit, you know, you get like 1.0003 or 2 or whatever that may be, I would say that's close enough. It could be off because you had to round these numbers. But if you're getting anything like 1.01, I would go back at that point and double check and make sure you rounded correctly, make sure you were doing the correct numerators and denominators on everything. If you didn't already add up your frequency column, make sure you add that up to make sure you didn't miss any data values or anything like that, or double count anything. Same thing on the low end. If you're at like 0.9998, that shouldn't be a problem. If you're getting like 0.98, that's a little bit more of an issue. So this is a relative frequency distribution. We're going to be looking at these quite a bit over the next couple weeks. And this is how you make one. So now we're going to look at visual ways to look at our data set. We're going to keep looking at this same data set. So the first thing we have here is a bar chart. So a bar chart is a visual representation of our data. Notice in our bar chart we have the injury types on this horizontal axis and the frequency on the vertical axis, and then we've got each of the injury type names that we saw in our table down here as well. So if we look at this first injury, if we look at the back injury, we can see that the rectangle over the back injury goes up to the 12. So that's telling us that there were 12 people with back injuries, which is the same thing that we saw from our data set. I could also, instead of having frequency right here, I could list this as relative frequency. If I wanted to do a relative frequency bar chart, that's totally fine. Examples of questions that I might ask you which one had the most injuries, which one had the least most. I might ask you how many more injuries did the doctor see with knee injuries as opposed to neck injuries. So in that case, you would need to look at how many knee injuries were there and subtract the number of neck injuries. I might also ask you how many total people were in the data set. In that case, you need to take the height of each bar, so figure out that one's 12, 2, 1, 2, so on and so on. Figure out the height of each of these bars, add them all up, and that's going to tell you how many total people were in the data set. Which for this one we know it was 30, but some data sets I may just give you a bar chart and no data or tables to go along with it. So you need to know how to figure out how many people were in the data set. The answer, by the way, is never going to be this number. Never. I will tell you that right now. If you put 13, you are wrong. You always need to look at the heights of each of the bars and add those up. Okay, that's pretty much it with bar charts. We don't do a ton with them, but they're pretty. I like pretty pictures. So now pie charts. We use pie charts even less than we use bar charts, but they're still useful. So pie charts you'll see a lot in the media, and it's important to know with pie charts that a lot of the times people will skew what their pie chart looks like to make what they want you to see look better. So that's just something to be aware of. And normally with pie charts, it didn't happen with this one because, to be honest, it just looked really funky. But you'll normally have some sort of percentage associated with each of the colors. So in this case, we've got a circle and it's been split up according to what percentage of the circle should be taken up by that injury. So here in yellow, we're looking at our back injuries. So the back injury was 40%. So 40% of this circle is colored in yellow because of back injuries. And I'm sorry the yellow is so hard to see. Okay, and then the wrist injuries, I believe, would be like 6.67% if I'm remembering those relative frequencies correctly. Okay, so sometimes it'll be in the middle, sometimes it'll be off to the side, especially with smaller sections like wrist, elbow, groin, neck. It's really hard to fit the percentage in the circle for that color, so sometimes they'll put them off to the side. That's pretty much it with pie charts. They're pretty easy to read. These should all sum to 100%. So you can use that in case, you know, there's like a missing value or something, hint, hint. But yeah, those are pie charts. Like I said, we don't really use them very much, but they're there. They're in the world. All right, and then the last one, this is the one that I think is the most interesting. This is a side-by-side bar chart. So what we have here is we have two different data sets. We have a data set from 1990 and a data set from 2013. And we were looking at the educational attainment of a sample of people in 1990 and then a different sample of people in 2013 to see how the relative frequency of people attaining these degrees has changed. So if we come down here, we can see on the graph, we've got a key here that says that 1990 is in blue and 2013 is in green. And then right here you can see where we have the relative frequency. So instead of the number of people earning those degrees, they've put the relative frequency of people that have earned that degree. Okay, So then you have all of the different types of educational attainment that they have, not a high school graduate, all the way up to a graduate or professional degree. So graduate or professional degree is like a master's or a PhD. Okay. So some really interesting questions I could ask are things like, which educational attainments did we see a decrease from 1990 to 2013? Well, what we're looking for is 1990 is in blue, 2013 is in green. So where did we see the green bar get shorter than the blue bar? Well, we saw it here with not a high school graduate, and we also see it here with some college and no degree. A little bit here with high school diploma, but that might be a good thing for if I were to ask you guys, which degree stayed the same from 1990 to 2013? That's where I would put these guys. I would say they're pretty much the same. I could also ask, what's the difference in the relative frequency for bachelor's degrees from 2013 to 1990? So in which case you would need to figure out what's the height for 2013, what's the height for 1990, and subtract the two. So just some examples of some questions that I could ask relating to those. And yeah, like I said, I think side-by-side bar charts are the most interesting because they allow us to compare data sets. And that's more fun than just looking at a single data set, in my opinion. And that's it for categorical data. So we're going to move on to quantitative data. So remember, quantitative data is data that comes to us as numerical values. So height, weight, age, number of credits you're taking this semester, number of pets you own, things like that. And another very important thing about quantitative data is it has to give meaning for us to add and subtract it. So even though my phone number is numerical, if I take my phone number and I add it to my sister's phone number, that doesn't tell you anything about us. But if I take my height and I add it to my sister's height, that would tell you how tall the two of us would be if I were to stand on her head, which she would not like, but I've probably done it before. Okay, so we want to be able to get some sort of meaning by adding or subtracting these numerical values. So the first thing we're going to do is a relative frequency distribution with our data. So the data that we have in here is in the Module 4 Part 1 Notes Quantitative now. And we have a data set. We're looking at the score of 20 students on a final exam. And one of the things that we can see when we look at this data set is we have a lot of different numbers. So if I were to just look at each individual number and list them out one at a time, I'd have a lot of rows in this table. And what we want to do with these tables is we want to organize our data. So having that many rows in my table doesn't really help me to organize it. So if you're looking in the notes, you're a little bit ahead, and you can see that I've created some groups. And I've grouped the numbers in groups of 10. So instead of looking at 50, 51, 52, 53, each as their individual row, what I'm going to do instead is I'm going to group them, and I'm going to do 50 through 60. Now I've created two different brackets next to these numbers. The hard bracket next to the 50 means that if I have the data value of 50, he is included in this group, or in this, these are also called classes. The parenthesis means that if I have the number 60, exactly 60, he would not be included in this grouping. He would need to be included in the next grouping, which is why I have a hard bracket and then a 60 through 70. And then hard bracket 70 through 80. And these ones, I just kind of grouped them based on what made sense. Because these were test scores, it makes sense to go by tens. Because if you go by tens, that's how we determine whether it's an A, B, C, D, or F. Okay, and I actually made one row too many, unless I skipped a number. No, that's fine. 90 to 100. And then I don't have any of these values, but if I did have someone who scored exactly 100, I would need this last row. I don't actually need it right now, but I have the row for it in here, so I'm going to use it. All right, so again, hard bracket next to the number means that number is included in this group. The parenthesis next to the number means it's not included in this group. So now from here, it's going to work exactly the same as it did for the categorical data. So I'm going to look at my data set and I'm going to find how many data values do I have in this range. So how many data values are there between 50 up to and not including 60? So basically for this one, it's how many data values are in the 50s. And there are 2, 50 and 57. Now I'm going to do the same thing. I'm going to look at how many values are between 60 and 70 in this data set. And again, there are 2. Now this one's a little trickier. 70 to 80. This is where you may want to put like a dot or a check mark or highlight as you go along and you're counting up how many values did we have in the 70s. Again, I don't recommend crossing it out so you can't read the number because we're going to need it later. So in the 70s we had 8 numbers. 80s to 90s there are 5. 90 to 103. And we don't really need this row, but I'll show you anyways. If you have a row in your table and there's no data values in that range of numbers, just put a 0. Don't skip over it. So if I didn't have any 70s or 80s, I would put a 0 there. I wouldn't go from 70 to, or from 60 to 80. I wouldn't want to skip over the 70s. I want to see that I didn't have any 70s. Okay, and now I can do a check and make sure that I didn't miss any numbers by adding up this frequency column. So 2 plus 2 plus 8 plus 5 plus 3, that equals 20. And according to the instructions, I have 20 students that I'm looking at. So that's good. That means I didn't miss anything. I'm going to come back real quick to the score column. So I mentioned I wouldn't want to skip from 70 or 60 to 70 down to 80 to 90 because that means I've skipped 70 to 80. So notice that the difference between 50 and 60 on the left, 60 and 70, 70 and 80, 80 and 90, 90 and 100, they all have the same difference between the number that's directly below them. So what I wouldn't want to do is I wouldn't want to do like this. I'm going to do it in another color. I wouldn't want to do 50 to 60, right? Kind of hard to see, I'm sorry. And then 60 to 80. Because now all of a sudden I have a difference of 20. So I've got 50 to 60 here is a difference of 10, but now here it's a difference of 20. I don't want to do that. I want to always have the same distance between my numbers. Oop, went one too far. Okay, so the difference between the first number of each group should be consistent all the way down. So this time I went by tens, so I need to always go by tens. If you decide to go by sevens, you need to go by sevens the entire time. So what I will say with this is make your life easier. Don't look at your data set and say, I'm going to go by 3.2. Don't make your life harder. Statistics is hard enough as it is. Go by 5s. Go by 4s even. Don't go by weird numbers when you're making these groups. Okay? All right, and then the last thing is the relative frequency column. This works exactly the same as it did before. We're going to take the number of people in that group and divide it by the total number of people that we were looking at. So 2 over 20 is 0.1, 2 over 20 is 0.1, 8 over 20 is 0.4, 5 over 20 is 0.25, 0.15, and 0. And then again, if I add up this column, it should sum to 1. So 4.65, 0.75, and it equals 1. Boom, that's wonderful. If it didn't equal 1, I would need to go back and double check and make sure that I did all of my math correct. If I had to do any rounding, that's where I would check all of my rounding. If I still don't find the mistake, maybe I need to go back to my frequency column and make sure that I have the correct number of numbers in each of those columns, make sure I didn't miss anything. stuff like that. All right, so now a visual representation of this data set. Kablam, we've got a histogram. We're going to see histograms quite a bit throughout the semester. So notice on this histogram, and I'm going to write over this real quick because you cannot read that at all. There's a 2 there. On this histogram, we have still our scores and our frequencies. And then right here, we've got the 50 and the 60, but the rectangle goes from the 50 to the 60. So this tells me that I have 2 data values from 50 through 59. So it does not include the 60, just like it didn't include the 60 in our table. But the interesting thing is I don't know what those 2 numbers are. They could be 55 and 55, they could be 2 50s, they could be a 51 and a 58. I have no way of knowing what they are if all I've been given is this histogram. Okay. So some things I could ask with the histogram, similar to the bar chart, what's the difference between the number of people who scored a C and the number of people who scored an A? So 70 to 80, 90 to 100. Which one scored the most? Which one scored the least? Things like that. Again, I could ask you how many total people were surveyed, in which case you would need to take 2 plus 2 plus 8 plus 5 plus 3 to get the total, which is 20. And from there I could ask you for some percentages. So I could say what percent of people scored between an 80 and a 90. So right here. So in that case you would need to take 5 over 20 and then multiply that by 100 to turn it into a percentage. Beyond that, that's pretty much it with the histogram. We're going to look at some more stuff with the histogram, but not quite yet. First, we're going to look at a stem and leaf plot. The stem and leaf plot is, in my opinion, the most complicated of all of the visual representations that we're going to do because it can drastically change depending on your data set. So what we want to do with a stem and leaf is we want to figure out the rightmost digit. So for example, in our data set, we have some numbers. I'm going to write a few of them down here. We have 74, 81, 77, 92, woohoo, and 50. I'm just going to write down those 5. So the rightmost number in all of these is the number in the ones place. So all of those numbers that I've underlined in blue are going to form our leaf. And now everything that I'm underlining in purple is going to form the stem. So our stem and leaf plot is going to start with a horizontal line, nope, a vertical line, a vertical line. So here's my vertical line. And my stem is going to consist of anything that is to the left of that rightmost digit. So looking at my data set, the smallest number I have to the right of my blue is a 5. And then I'm going to have a 6, 7, 8, 9. And if I had any numbers in the hundreds, I would have to write 10. Now I need to put in my leaves. So these are all of the values that I underlined in blue, and it's for all of the numbers throughout the entire table. Okay, so we'll start with these ones that are in front of us here. So we have a 74. I'm going to do blue, keep it consistent. So I'm going to put a 4 next to the 7. I have an 81. So a 1 next to the 8. Now I have 77. So next to the 4, I'm going to put a 7. And then 92 and 50. And now I'm going to go back to the full data set and I'm going to finish filling in all of the numbers. So I stopped at 50, so then I have a 72 and then a 68, 83, 76, 72, 80, 82, 75, 83, 62, 57, 77, 93, 94, 73. All right, so that's all of the numbers. So the number in the ones place is on the right, and the number, any numbers left of the ones place is on the right, or on the left, I'm sorry. So everything in purple, those are my stems. Everything in blue, those are my leaves. So that's the stem and leaf, but we want to do one more thing with this. We always want to put our leaves in numerical order. So if we look right here in the 60s, I've got 68 and then 62. Well, 68 comes after 62, so what I want to go ahead and do is I want to go ahead and flip-flop those. So I want it to read 2 first, and then the 8. So I want to put these leaves in numerical order. So we're going to go ahead and do that, and I have the answer in front of me, so I'm going to just write them down. You could erase like I'm doing, or if you have a lot of them, and you have the room for it, you can just go ahead and create a second stem and leaf with these guys in order. This also makes it a little bit easier to see where I have repeats. So I can see here a lot clearer now that I have 2 72s and 2 77s, whereas that wasn't quite as clear to me before. Same thing down here, I had 2 83s, and it was a little hard to tell that because they weren't directly next to each other. And then 2 3 4 are already in order. Perfect. So this is my stem and leaf, and then there's one more thing I can do that's optional, is I can create a little key over here. Because it's not always going to be that our data set is 1s and 10s. Sometimes it might be one number past a decimal point and then everything to the left of the decimal point. Or it could be things in the thousands is to the left, and then the ones place is to the right. So what I'm going to do is I'm going to say 5/0 equals 50. And that way I know that I'm looking at the number 50, not the number 5.0 or 5.7. I'm just looking at 50. I hope that makes sense. I anticipate a lot of questions on stem and leaves, to be completely honest with you guys. So, because I think they're complicated to learn, but once you learn them and you understand them, they're not so bad. So now if we look at our stem and leaf, we can see that it actually looks pretty similar to the histogram that we had on the previous page. I'm going to go back to that. So our histogram, we had 2, 2, 8, 5, and 3, and we could kind of see the peak, which is the one with the highest right here. This is our peak, okay, and then everything coming down around it. And we can see the same thing here. We've got this peak in the 70s. But what the stem and leaf is doing with us that the histogram doesn't is I can see that the numbers in the 50s were a 50 and a 57, which if you remember before over here, all I knew is that I had 2 numbers in the 50s, but I didn't know exactly what those 2 numbers were. With the stem and leaf, I can see exactly what those 2 numbers are. They're a 50 and a 57. There's no muss, no fuss about that. So that's the really big advantage with a stem and leaf. Alright, so the last thing with this section is we're going to look at shapes of distribution. So this is going back to histograms. A little bit stem and leaf too. You can identify the shape of a distribution from a stem and leaf as well. So, but we're going to look at histograms with them because they're easier to draw. So a uniform distribution occurs when our histogram, the frequencies are all the same. They're very boring. Okay, so let's say this is a height of 2. And let's say I asked my class, how many pets do you have? Okay, so this is a histogram that represents the number of pets. I'm making this up. I do not actually expect that this is what it would look like. But we'll say I have 2 students that told me they had 0 pets, 2 students said they had 1 pet, 2 students have 2 pets, and so on and so forth. So there's no variation among the data in my data set. The biggest time that I know of that we see uniform distributions is in probability. When we're looking at rolling a die and things like that, they're going to have a uniform distribution. In nature, in the real world, I cannot think of anything that is uniformly distributed. There's always a little bit of variation in there. So, your book probably had an example that I just didn't read or didn't remember. Alright, so that's a uniform distribution. We're not going to see a whole lot of that, but it's there for us to know. Now our bell-shaped distribution. This is the one that we are going to see so much of. It's going to become your best friend, and every semester I tell my students this, and they do not believe me until it happens. And then they're like, wow, you weren't kidding. We're going to see this distribution a lot. So a bell-shaped distribution, also called a normal distribution, looks like this. So we have a gradual increase from left to right at about the middle. We're going to call that the middle. We see our peak or our highest one, and then they taper off from there. So if I take a line and I draw a line over this, it kind of looks like a Christmas bell. And our peak is right in the middle. Okay. So when we're talking about these distributions, if I ask you to draw me a bell-shaped distribution, what I'm looking for really is this line. I'm not necessarily looking for the histogram that I drew underneath it, but you need to remember that there is going to be a histogram about your data underneath this line that we're drawing. Okay, so an example of a data set that might look like this is IQ scores. People's IQ scores are normally, bell-shaped. Most people have an IQ score of about 100. There aren't very many people way out here with an IQ score as low as 70. And there aren't very many people with a high IQ score around 130. So most people are clumped in around 100. And then it starts to kind of taper off with the amount of people on either side as you get further below 100 and further above 100. Like I said, we're going to see this distribution a lot. You will become very familiar with them. And we're also going to see IQ scores as examples all the time. It's one of my go-tos. All right, our next distribution is a skewed right distribution. So again, I'm going to draw the histogram underneath it so that you understand what's happening with the data, but then I'm going to draw the line over it, and that's what I'm really looking for you guys to draw with these. So a skewed right distribution, the peak occurs to the left of the middle, and then we get this long tail that happens off on the right. So we're going to keep going, keep drawing that tail. Boom. So if I draw a line over that, we can see here's our peak, and then we get this long tail. And notice the tail is off to the right. That's why it's skewed right, because the tail is on the right, and our peak is on the left. And I'm repeating that, tail on the right, peak on the left, because I did not ever understand that when I learned this. It took me the longest time to figure that out. And if someone had just told me it's the side that the tail's on, tells you which skew it is, I probably would have gotten it a lot faster. Okay, so this is skewed right. An example of a skewed right distribution would be speeding tickets on I-25. Most people, when they get pulled over, they're going probably about 70 miles an hour, maybe 80 miles an hour when they get pulled over. Okay, but then you have that one person or two people that get pulled over going like 130, like somebody apparently up in Greeley yesterday got pulled over going 130. Okay, so this person with 130, they're going to make the skew to the right because they're much higher than the rest of the people driving around Denver. And the last one is skewed left, which is the exact opposite of skewed right. So we have a tail over here on the left. This is starting to look funky. And then our peak is going to happen to the right of the middle. Maybe like right there is where our peak will happen on this one. Okay, and I draw my curve over it. So again, here's my peak. And my tail is over here on the left. So it is skewed left. An example data set for this would be potentially test scores. We try and make test scores bell-shaped, but it doesn't always happen when somebody decides not to show up. So this person got a 0. These people got Fs. Okay, but most of the class is over here at like a C to an A. Okay, so most of the people who took this test, they've been doing well, they've been showing up to class. You just have a few slackers over here getting Fs, didn't even show up for the test. Just whatever's happening with them. They caused it to be skewed left. Okay, so those are our distributions. So again, I'm just going to go back real quick. We've got the uniform distribution, a bell-shaped distribution, skewed right, and skewed left. So that's everything for this first lecture. This lecture is probably one of the longer ones we're going to have at over 40 minutes at this point, but there's a lot of information to get through in this first section of notes. So at this point, if you have any questions, please feel free to email me those questions. Also, if you have any feedback on this video for me, either you think I talk too fast, if you want me to use more colors, if you couldn't see any of the colors that I was using in this video very well, if just whatever you want to let me know. If there was something in the video that you didn't like that I did, or if there was something in this video that you did like. This is a new program that I'm using to create videos this semester, so I'm still trying to figure out some of the kinks, and maybe you heard my cat in the background just now. He's being very noisy. So go ahead, start on your homework on My Open Math. Hopefully you've created that account. If not, this is a great time to go and do that, and I will see you guys in the next video.